It turns out that molecules actually are going to collide with each other. You have some gas, and it's inside of a container. Then obviously these particles, if you have enough of them in there, then kind of statistically they're going to, perhaps that one's moving that way and that one's moving directly at that one. Statistically they're going to collide with each other. We can talk about the mean free path of the molecule, which is essentially going to be an average distance that it travels between colliding with other molecules, and the average time between collisions is going to be called the mean free time. These are related to the speed of the particles. So it'll also be related to the pressure inside of the chamber as well as the temperature. And we can express this as such, but really I'm not going to hold you accountable for knowing those equations. So now let's talk about what happens when we add heat to gases. We already know that if we have a large object and we add heat to it, essentially it's going to change the temperature. The change in temperature is going to be related to the mass of the object multiplied by the specific heat. So the more massive an object was and the higher the specific heat, the less the temperature went up for a given input of energy. For gases, now we're not talking so much about the masses, we're talking about the number of moles right here. And we're now talking about a molar specific heat, but really it behaves the same way as the specific heat before. If we add heat to an object, the change in temperature is going to be related to the number of moles as well as the molar heat capacity. Now this molar heat capacity is actually going to be related to the type of gas that we're adding the energy to. If we consider a monotonic gas, what I mean by monotonic, I mean just a single element, so no bonds are going on here. This monotonic gas has 3 degrees of freedom. That means that it can move to the left or to the right, that's 1 degree of freedom. It can move up and down, that's another degree of freedom. And it can move into and out of the page. Now all of these are going to be related to the velocity, so you increase the heat of an object, or you give some heat to this molecule, and it's going to change its kinetic energy, it's going to change its velocity, it's going to also correspondingly change its temperature. If we consider a diatomic gas, what I mean by diatomic, I mean more than one element. So if we consider the element N2, we're going to have 2 nitrogens that are bound together kind of like that. So this would be diatomic nitrogen. You add energy to this guy, and it can go left-right, it can go up-down. So there's 2 degrees, it can go into and out of the page. There's a 3rd degree of freedom. It has a 4th degree of freedom, it can rotate. And it has a 5th degree of freedom, it can vibrate back and forth. So it has 5 degrees of freedom. If you add energy to this particle, it's actually going to have an equal amount of energy go into all 5 degrees. It's called the equipartition of energy. However, the rotation and vibration, what that means is, those are going to take away some of the energy that goes to the velocity, so it's going to be actually harder to increase the temperature. So this object increase the temperature of a diatomic molecule. What that means is this molar specific heat is going to be higher for a diatomic molecule, and it turns out that it's related to the degrees of freedom divided by 2 multiplied by that R right there. So here we have the molar specific heat for an ideal monotonic gas. You can see the 3 is related to the 3 degrees of freedom. You can see the 5R divided by 2 is going to be the specific heat for the diatomic gas, where that 5 is related to the degrees of freedom. It's going to be higher specific heat for a diatomic gas because some of that energy goes into rotation and vibration and not into translation. So for a given input of energy, the temperature is just not going to rise as much. Here's just a little chart on table 18.1 that shows the several monotonic gases and several diatomic gases and their molar heat capacities in case you ever need these guys. So we can actually talk about the speeds here. If we add some heat, we're going to add some energy to our gas, we're going to change the temperature. So we can talk about the molecular speeds. The derivation of this distribution of speeds is based on statistical mechanics and a little bit beyond the scope of this class. It's called a Maxwell-Boltzmann distribution, and really it just says, okay, this gas is going to have a distribution of speeds inside of it. Not all the particles are moving at the same exact speed. The real key to this guy is to say, I know that this speed is going to be related to the temperature, and as if I look at this is going to be a distribution of velocities right here. If I increase my temperature of my gas, this most probable velocity is going to increase, and actually the distribution is going to slightly widen. So I've already shown you a nice little pressure volume diagram, so now let me show you a very quick pressure temperature diagram, where here I'm plotting pressure on this axis and temperature over here. You kind of know that we're going to have three phases of matter. We're going to have solid, we're going to have liquid, and then we're going to have gaseous or vapor phase. And if we think about, let's just say, water, and we pick a volume, say we have a certain volume of water. If the temperature is really low, close to zero, then all that material is going to be in the solid phase. It's going to be ice. If we add some energy to it, we're essentially increasing the temperature. At some point right here, we're going to have that fusion that I talked about last time, that latent heat of fusion. Eventually all that liquid goes into, or all of that solid goes into a liquid. You keep on increasing the temperature, adding energy to it. It's going to undergo vaporization. We have the vaporization curve right here, and then it's going to go into the gaseous phase. Now it turns out that this is going to depend on both the volume and the pressure. If the pressure is higher, then this temperature is going to the temperature at which the fusion and the vaporization occur is going to be slightly different. You know that if you try to boil water at altitude, or at a higher altitude, go out to Colorado, it's going to boil at a different temperature. It's going to boil actually at a lower temperature, so you need to cook things for longer at altitude. Similarly, if you increase the pressure, it's going to increase the temperature at which the solid becomes a liquid, and it's going to increase the point where the liquid becomes a gas. We can of course make this a little bit more complicated and say, well, you know that from the ideal gas law, we're going to have pressure times volume divided by temperature is going to be equal to a constant. On the last slide there, I showed you a pressure temperature diagram, so this one right here, where we had solid, liquid, gas. I've talked about pressure volume distributions, where I said we pick a constant temperature. We can actually draw a even more complicated diagram, where we're going to have pressure here, volume here, and temperature here, and look at how pressure, volume, and temperature all change at once.